welcome back to my YouTube channel. This video, it will be a continuation for our Form 5, Chapter 4, and this time round you see grid line for the purpose of discussion. For this time round we are going to do Cathode Ray Oscilloscope. Okay, Form 5, Chapter 5, Part 2. We will do Cathode Ray Oscilloscope. Okay. Now, previously, I've gone through how do you get electron beam, and you have seen that I prove it to you. Oscilloscope. Okay, you have seen that when the electron gone through the tube, it hit onto a Maltese cross and eventually form an image. This electron beam would be a conserved energy, where joule electron volt equals to half mv squared. All of this electrical energy is fully transferred into kinetic energy that obey the conservation law of energy. And you have seen also the unit electron volt is actually equals to joule. Just as it tells you this is electrical energy. Now, as for oscilloscope, from your school, I hope you have really be able to get a chance to operate it. The cross-sectional view would look like this, where it starts off with, again, heating element, where this is where the filament is being heated up and it grows into normally yellowish color. So hot that increases temperature, and then they will have a piece of metal. This metal is being heated up by this filament, and then what happened, this metal is subject to really high potential. Okay, so where you have a focus, they will be focused over it. But before that, they would have a control grid. This control grid is designed so as to control the brightness of the spot. If you have only one, let's say you have only one electron beam pass through it, then will control the amount of electron it will pass through and then hit onto the wall, hit onto the screen. This is your screen. So in order to do that, in order to actually change it, whether to change it to left, right, up and down, scientists in the past actually made some improvement. One would be to include the Y channel as well as with the X channel or the X plate. So this would be the Y plate. This is to make sure you have provide positive and negative potential difference. Then the beam would go up or travel upwards eventually. Or you have the other plate called X plate, so that the image you can't see, I can't really draw it here, so I'm going to redraw that screen. I can redraw it this manner. So this is a grid line we use. If we X plate, then the beam will go left to right. The Y plate is going to make this light dot, this dot, go up and down. The combination of the both, this is caused by the X plate, this is caused by the Y plate. Combination, if X move and Y also move, what happened? You will get a sinusoidal wavefront. Okay, and then this whole operation is performed under vacuum, so that the electron beam is going to prevent the electron collide with air molecule. And then this is where the screen, where you have phosphorescent screen, so that you produce light. Okay, now the electron cathode ray, these are the cathode ray. This cathode ray is actually the beam of electron moving from the filament. What happened? Let me show you next page. This is one of the example where I have a nichrome wire. This is actually nichrome wire. Nichrome wire is famous with its really high resistance. So what happened, I provide current pass through it, this end, and to out the other end. As I increase the current, what happened? The resistance builds up and it generates heat, and therefore it grows. Okay, it's theoretically the temperature is growing. The temperature could reach up somewhere about 300 and 350 degrees C. That's why it's growing yellowish, reddish, this line. Okay, the same is true. The same effect is happened here, inside here. The same effect. They use maybe not nichrome, maybe they use tungsten because of its really high melting point. Then you can get an electron beam. You heat it up, and then provide potential, and then you form an image over this screen. Now, one of those typical example that you will find from your reference or textbook or my video, after watching it, you are supposed to go through the example to be sure that you have some idea what's going on. Now, say for example, if this were to be the screen, okay, of the oscilloscope, you would normally see question like this. Like for example, you have, say, you have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Okay. Say this is one of the example, and then what happened? They will give you, a knob, a turn knob. They give you a scale, watt per centimeter. Okay, and then they give you, oh, okay, one of two. It's 1 cm. Scale. Okay, 2 squares is 1 cm. Then it is pointing at perhaps 1.5. You have 1.5, you turn up the knob, you may rotate the knob to turn it to maybe 1.5, 2.0, 2.5, etc. You point at 1.5 watt per centimeter, and this is the wavefront. Then you will ask, okay, what would be the peak voltage? Right? I hope you have seen it in some of those books. This will be an example. So quite obvious, peak voltage. Peak is from top to, this is at equilibrium. Okay, peak up, it's 1 cm. So therefore, 1.5 volt. Rather straightforward, right? Let me show you another example. Let's have, the previous question is on the Y plate. Obviously this is a Y plate. Okay. How about another example? They're going to show example for maybe time. The X plate. Okay, this is a screen. Let's focus at this screen, and we have, say for example, perhaps now I have again this 1, 2, 3, just a rough draft. 1, 2, 3 up, 3 down, 3 up, and 3 down. Okay, 3, 3 is a 3, 1, 2, 3, 1, 2, 3 is right from equilibrium. Now, you may continue sketch it so that it looks perfect, okay, etc. Now, how about now you were told this is a wavefront for alternate current, obviously, sinusoidal graph of the current, where this alternate current is connected to a CRO, Cathode Ray Oscilloscope. Then this is what will happen. And with the time base adjust, you are told the time base, it is set at 5 milliseconds per centimeter per cm. Then yeah, you were told now 1 square, just now was 2, now it's 1 square 1 cm, left right, up and down the same. Okay, 1 cm 1 cm. Okay, so this is a perfect square, 1 cm and 1 each side. So now the question is, how do you find the frequency? Okay, now question like this, come back to the definition. Frequency. Frequency is defined as number, this symbol is number of wave over time taken. Then you will ask, what does it mean by that? Right? So, therefore, number of wave over time. Let me show you how to measure number of wave. The easiest way is to find out how many wave make. Let's say for example from here to here, this end to this end, this is 1 wave, this is 2 wave, and this is 2.5 wave. You may measure only the 1, but I want to show you how do you actually use number of wave. So I'll make use of 1, 2, 3. Or another way to recalculate the wave is every half, you measure how many half, 1 half, 2 halves, 3, 4, 5 half wave. Okay, so there are 5 half waves. So therefore, number of wave frequency, there are 5 half wave. There are half wave. If 1 wave is 1, half wave is half. Okay, so wave, it doesn't need to have the wavelength. No need. It's just how many wave. It's just 5 of half over how long does it take from this point to that point. this point to that point. This 1 square, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 centimeter, 1 centimeter, 5 millisecond. So 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 1 is 5 millisecond. Right? So you cancel that 5 and 5. So therefore it turns out to be, now milli is minus 3. So you put it into calculator, that would be 50 Hertz. Okay? Or you have another way of doing it. Let me have a look. Okay. How do you get it? Let me show you. This is cancel off already, so therefore you have 1 over 2 and 10 is 20. Milli is times 10 minus 3, so therefore it would be minus 3 and divided by minus 3, so it would be 1000 over 20. So therefore Hertz cancel off, it will be 50 Hertz. Okay, so this is the maths include that you need. And I've gone through 2 examples already. So this example where you have the X plate and the Y plate together. This is where we measure only the Y plate. And you should actually go through at least 5 to 10 questions on Cathode Ray Oscilloscope to actually calculate the time base and also the height base, the peak volume or the peak voltage that you have. It will always be how the electron moves caused by the external field, external to it. Using the famous standard left-hand Fleming rules. That's all from me in this video. It will always be true that you will need to go through your reference or exercise, chapter by chapter exercise, Form 5, Physics. For Cathode Ray Oscilloscope, I would suggest to go through at least 15 questions, 15 to 20 questions, before you proceed to my next video. I thank you and appreciate the thumbs up button. Stay tuned to my next video.